Hello and welcome to the Plant Breeding and Genomics Community of Practice webinar, an introduction to the Augmented Experimental Design. My name is Heather Merck and I'm the Content Coordinator for PBG and your host today. For those of you unfamiliar with the Plant Breeding and Genomics Community of Practice, aka PBG, I invite you to explore our training resources at www.extension.org/plant_breeding_genomics. I also invite you to subscribe to our newsletter, PBG News, to stay up to date with PBG webinars and other news. You can sign up at pbgworks.org. During today's webinar, Dr. Jennifer Kling of Oregon State University will provide an introduction to augmented designs and perform sample analyses using data from her Meadowfoam breeding program. Please note that today's webinar is intended to be an introduction to the augmented design. We are planning a future webinar focused on more complex analyses. Today's presentation, as well as Dr. Kling's dataset and SAS program, are available at extension.org/pages/60430. Please now join me in welcoming today's presenter, Dr. Jennifer Kling. Dr. Kling is a plant breeder who teaches experimental design to graduate students in agriculture at Oregon State University. She has considerable experience in the application of recurrent selection methods to improve yield, stress tolerance, and disease and insect resistance in cross-pollinating crops. She enjoys analyzing data and was the data curator for the Barley Coordinated Agricultural Project. Dr. Kling received her bachelor's degree in crop science from Oregon State University and her master's in agronomy from the University of Nebraska-Lincoln. She obtained her PhD in genetics with a minor in statistics from North Carolina State University. I'll now turn things over to you, Jenny.
Okay, well, thank you for that introduction, Heather. I'll start by giving an overview of the presentation today. I'll first describe the essential features of augmented designs and when we use them in plant breeding. We'll talk about some of the design options, and as Heather mentioned, today we'll look more closely at a simple case where we have just one-way control of heterogeneity. I'll give a specific example from my breeding program. We'll talk about how to do the randomization and field plan, how to analyze the data with SAS, and how to interpret results. We'll also give a brief overview of variations on the basic design that you may hear about in future webinars. And finally, we'll talk about some software that's available and further references. Augmented designs were first introduced by Dr. Federer in 1956. Essential features are that check varieties, the controls, are replicated in a standard experimental design, and you generally have 2 or more controls. Also, you have a number of new treatments. In our case, those would be genotypes that are not replicated or have fewer replicates than the checks, and so they augment the standard design. It's helpful to look at what was in place before augmented designs were widely adopted. So I've chosen an example here from breeding for striga resistance in sorghum at ICRISAT. This is from a publication in 1983. They used then the systematic arrangement of checks. Striga in sorghum is particularly notable for the variation. It's quite influenced by local soil conditions, and so it's very essential to have some sort of local environmental control in the field. In the initial stages in the observation nursery that were unreplicated, they would include a susceptible check that was repeated at constant intervals throughout the field. After that, they would go to replicated trials, and they would have one particular susceptible check that would be surrounded by 8 test plots, and they would use that susceptible check to adjust the observations on the test plots. In the final, more advanced stage of screening, they would actually use a susceptible check every other plot. And you can see that this is quite resource intensive in that there's a lot of the area in the field devoted to the check plots that you cannot use for your selection. So the advantages of augmented design, one is that you can use fewer check plots than would be required for designs with systematic repetition of a single check. Additionally, you get an estimate of standard error since you have several checks in the trial that can be used for comparisons. You can make comparisons among new genotypes or between your new genotypes and check varieties. You also have a means to adjust your new genotypes for the field heterogeneity in the field. There are some disadvantages. You are still spending some resources on production and processing of your control plots. You still need those control plots. Also, you have relatively few degrees of freedom for your experimental error, which means that you may not have sufficient power to detect differences among treatments if it's a trait that's not highly heritable. Also, unreplicated experiments are inherently imprecise, no matter how sophisticated the design. So when would we use them? In early generations, when seed is limited, we may have too many new entries to replicate, or it may be difficult to maintain homogeneity within our blocks because we have so many entries to look at. They can also be used in on-farm research. Growers may prefer to grow a single replication and they may not be able to accommodate all of the entries in the experiment. So, basically you have to make several decisions. You choose a design that's appropriate for controlling the heterogeneity in the experimental error. You can choose to use one-way blocking with a completely randomized design, or you may choose to use an incomplete block design. Or you may choose to control heterogeneity in two directions using a Latin square or an incomplete two-way blocking experiment such as a Uden square or a row column design. So you have a number of design options. You can, and it's important to remember that the underlying design refers to the assignment of checks to the experimental units. All augmented designs are incomplete with respect to the new entries, and so I think in some cases people may believe they need to use say a lattice design because they have a lot of new check entries, but actually the important point is to consider how many checks you have in the experiment, for example. It's also possible to replicate these designs in different environments. At that point, once you've committed to doing replication, you may need to consider other options such as lattice designs and compare the relative efficiency compared to those designs, and also consider your particular objectives. Okay. So I'm going to discuss one particular augmented block design example, the very simplest case where we're only controlling heterogeneity in one direction. We want to, the checks occur once in every block, and the new entries occur just once in the experiment. So this would be called an augmented randomized complete block design. And the example I'm going to give is from the crop that I breed. It's called Meadowfoam. This is a native plant that was first produced as a crop in Oregon in 1980. It's grown for its seed oil, which has very novel long-chain fatty acids. It makes it have exceptional oxidative stability. Presently, it's used in cosmetics, but it also has potential uses as a fuel additive, as an additive in vehicle lubricants, or in pharmaceutical products. And you can see on the right there that the seeds are quite small. Meadowfoam is a very good rotation crop in the Willamette Valley of Oregon. It's a winter annual, so its production cycle fits in very well with the weather and rainfall patterns that we have here. The plant and seed meal are high in glucosinolates. It's a member of the brassicales, and the glucosinolates are thought to have some phytosanitary properties. Another advantage is that it fits very well into the grass seed productions, which are predominant here. You can see in the picture below there the windrows that are being harvested of Meadowfoam using the same equipment that you would use for grass seed production. There are a number of pollinators that can be used for Meadowfoam. Commercially, the growers would rent honeybee hives. But for the breeding program, we've recently figured out that we have a couple different options. We could also use blue orchard bees, which work very well in small isolations or in small cages. We also can use blue bottle flies in the greenhouse to do small recombinations, or, as you see here in this picture, to self large numbers of plants. The particular germplasm I was working with, this was in 2005, I had inherited some diverse breeding populations from a retired breeder. Those populations, we'd regenerated the seed at the greenhouse and selfed a large number of plants. We had, after 2 generations, we had S2 lines, and we transplanted those lines to the field, and they were allowed to outcross. This is the first time that we had tried using an S2 test cross system in Meadowfoam, so I didn't have all the details worked out, and we didn't have sufficient seed for replicated progeny trials. Our goal was essentially to form a broad-based population for recurrent selection, so we wanted to screen the S2 test crosses and then select the best S2 parents for recombination. So we did actually a couple of different experiments that year, but I'll talk about one of them. One of the augmented designs was included 50 new S2 test cross families that had never been tested before. We had 3 Czech varieties. The first 2 you see there, Ross and OMF 183, came from our elite population, OMF 58, and represented 2 different cycles of selection of that elite population. We also had a variety Starlight, which had been commercially released and had been derived from the same germplasm pool that we were evaluating. So we wanted to be sure to compare our new entries to Starlight to ensure that they would be superior to what was already available. So as I said, we decided to block in one direction. We had these 3 checks. And so we chose to use 6 blocks. We played around a little bit and realized that would give us error degrees of freedom of 10, which is pretty much the minimum that you need to be able to detect differences unless you have a very highly heritable trait. We had the 50 new entries. So the total number of plots was, including the replicated checks and the new entries, was 68. This came out to about 12 entries per block, but since we only had the 50 new entries, the last block only had 8 plots, and that was okay because one nice thing about the augmented designs is that you don't have to have equal numbers of new entries in every block. So here's our statistical model, and I included a residual plot. I just ran, and initially I just ran an ANOVA, and included a residual plot here to make a particular point. You can see along the 0 axis there that these are our new entries, and they actually have no residual. They're contributing nothing to error. The other plots that you see represent the check plots. And essentially what you're doing here is, the estimate of error you're getting would be the same if you didn't include the new entries at all. You're essentially doing a design on the check entries and then using the information there to adjust for the block effects and adjust the values of your new entries. So in your field plan, you need to be sure to include a sufficient number of checks and replicates to get a reasonable estimate of experimental error, so you can detect differences among your varieties. As in any design, you'd want to arrange your blocks along the field gradient to get the most possible variation among blocks and minimize the variation within blocks. You have to assign each of your checks at random to each block, and then after that you would assign your new entries at random to the remaining plots. There's also an online tool for to generate a randomization. I just use random number generator in Excel to do mine. It's not hard to do, but that online tool is available. Okay, so here shows the field layout. We have our 6 blocks along this dimension here, and then we have within each block we have 12 plots, and I usually number them in a serpentine fashion. And then in the block 6 we did not have a complete, we didn't have the 12, we had 8 plots. So the first thing you would do then is go ahead and assign at random your checks to those experimental units. You'd put all 3 checks one time in each block. And then you would randomly assign your remaining entries to the remaining plots. And this is a picture showing what a typical Meadowfoam progeny trial looks like. This is just shortly after flowering. For data collection, we collected information on flowering dates, plant height, disease resistance, lodging, seed yield, 1,000 seed weight, and we weren't able at that time we didn't have a capability then for large-scale screening of oil content. We do have that now, and it's a routine measurement. Of course, it's our primary interest. For this example, we'll just look at the variable 1,000 seed weight. It has a relatively high heritability, and it's positively correlated with both oil content and oil yield. Okay, one important decision that has to be made before you begin the analysis is to decide whether your genotypes are going to be fixed or random. It's generally assumed that our blocks are random because they represent a larger group of potential blocks, and we want to be able to make inferences beyond the particular sample of blocks in the experiment. For the genotypes, we know that the checks are fixed effects. We're wanting to make specific comparisons with those varieties. However, the new entries could be fixed or random. Most commonly, they're considered to be random because they've never been evaluated before. However, in this case, you could argue that they would be fixed. You want to make specific comparisons and to select the winners, and also they didn't come from a common population. So we'll go ahead and look at the analysis, both of these possible analyses. Okay, so let's start out just considering our genotypes to be fixed. This is showing the format you could use for data entry. This is the simplest way where you actually put the data directly into your program. So in SAS, you would need to assign a data name to that data set. And then you would use an input statement to indicate the order that your entries are occurring. You notice that we have a $sign with the name variable because that includes a character variable. And then you would just simply list your data lines. There's other options for data input in SAS, including using the import wizard. You could use in-file statements, or you could set up a SAS library. But this is just a simplest approach. So for the first analysis, I'm going to use the mixed procedure in SAS, assuming that our entries are fixed. So we need a class statement to indicate that block and entries are both class variables. In the model statement with proc mixed, you only include your fixed effects. So the model statement is saying the 1,000 seed weight equals entry. And then in this case, we have blocks are random effect. You notice in this case, since the entries are all fixed, we don't really need to distinguish, at least at this point, between our checks and our new entries. So if you're going to do all possible comparisons among your entries, you need to take some kind of precaution to ensure that you don't inflate type 1 error. So I've used in my LS means statement there, I've used a Tukey adjustment to allow for all possible comparisons. Another option, since we are primarily interested in comparing the new entries to Starlight, which was entry number 91, is you could use the control upper statement, and in that case I'm essentially doing a Dunnett test because I want to compare everything to control. So to control the experiment-wise type 1 error, I use the Dunnett adjustment. You can, in SAS, is quite convenient. You could sort your output in any way that you wanted to. I am quite comfortable with Excel spreadsheets, so what I generally do is simply create new data sets and then export those data sets using the export wizard to Excel, and then I sort them or make selections or do whatever I want to from there. So the ODS output is essentially creating new data sets for you. So I'm creating one that includes the adjusted means, and then another one that shows the results from the multiple comparison tests. So here's the result for that particular analysis. You see up at the top there the estimates of the variances for the variance components for blocks and residuals, the random effects. And then below that is a log likelihood. And in the sample SAS program that I provided, you can, for example, if you wanted to find out if blocks were important, you could run a model, a reduced model without blocks, and then take the difference between the log likelihoods from the two programs and use that to test for the significance of the block variance to see if it's greater than 0. Generally speaking, we would want to make adjustments to our means if we get any kind of estimate for our block sets greater than 0. So we will go ahead and do that. We have a test of fixed effects here for entries, which shows that there are highly significant differences among our entries. At this point, we don't know if that's due to differences among our checks or among our new entries. So this is just showing after I've, for example, exported the multiple comparison test results to an Excel file. I could open that up and look, and the, for example, the first line here shows the comparison between entry 1 and Starlight, which is entry 91. And so this would be the difference between those observations. And then over on the far right here, this would be the probability value for the Dunnett test. Now this is quite a conservative test, so if you are more concerned about making a type 2 error, which is throwing out a winner, than you are about making a type 1 error, you do have also here in the output a column that shows results from a standard type of LSD test. So we see, for example, one entry down here is significant using the Dunnett's test, significantly better than Starlight using a Dunnett's test, and then there would be others that we could consider using just a standard LSD test. I think it's important to make the point that there are different standard errors when you're comparing, say, one check versus another check. That's the most precise comparison. New entries versus the check, or if you're comparing entries in the same block, that comparison will be made with more precision than if you're looking at new entries in different blocks. Okay. So for the second analysis, we want to consider that our new entries are random effects. So I used the SAS code from this reference here, Wolfinger et al. In 1997. You could also just do this manually in a spreadsheet. Essentially what you're trying to do is you're creating an indicator variable called new that we give a value of 1 when we have a new entry and a value of 0 when we have a check. And then we also create another variable called, I'm calling it entry C here, which is collectively is 999 for all of the new entries, but then maintains the actual value for the check varieties. For example, MF183 is entry number 90. So this allows us then to make comparison among our checks and then a collective comparison between the mean for the new entries and any of the checks. Okay, and so if you didn't want to do that manually, you could use this little routine here to create a new data set in that format. Okay. Initially then, I just ran this to get an ANOVA. I used the GLM procedure. And so the difference between GLM and proc mixed is that in GLM, in your model statement, you include all of the factors in your analysis, whereas in proc mixed, you would only include your fixed effects in your model statement and your random effects in your random statement. So in this case, I'm just doing ANOVA. The solution option here indicates that I want solution for the fixed effects. And so then the output from that analysis is shown below here at the ANOVA. We can see here that we do have significant variation among our blocks. The checks actually were fairly comparable to each other, so there's not significant variation among the checks, but we see from the new times entry probability value here that indicates that we have significant variation among our new entries. Okay, so then to go on and use the mixed procedure to analyze the entries as random effects. The analysis would look like this. We'd have our class statement here with block entries and the new fixed effect value there. And in the model statement, we only would include our fixed effects, being the entry C. And then we could request the solution for the fixed effects. In the random statement, we would include the two random components and also request a solution for the random effects. And then we would get request means for our check entries. And then, as I did before, I would create a new data set that was the output of essentially the solutions for the random effects. I'm calling them the eBLUPs. And then you could use the export wizard to export eBLUP to an Excel file or CSV file or whatever you wanted to use. So here's the results for the second analysis there. You see we have the estimates of our variance components up at the top for blocks, the new entries, and then the residuals, and that there is a reasonable variance among our new entries. Again, we have then the fit statistics, which we could use if we wanted to compare one model against another. And then at the bottom there, we have a test of fixed effects. This includes all the three controls, and then it also includes the average of all of the new entries, and that's why we have 3 degrees of freedom. So you can see here that there actually isn't any significant variation among the controls. So this is looking then at the Excel file I created by outputting the eBLUPs. At the bottom there, you see all of the estimates for the new entries. For example, the 0.2991 indicates these are deviations from a midpoint, so that was better, that had larger 1,000 seed weight than the average, and so on. If you would prefer to look at these on the original scale, you could go back up to your solution for fixed effects and use your intercept value. So you would simply add then all of these estimates onto your intercept value to get the BLUP estimate that you could use for selection, for example. Okay, now there are a number of variations that we don't have time to go into today, but I will give you sort of a lead, and then there'll be more discussion of this in future webinars. For example, if you wanted to control variation in 2 dimensions, you could use a modified Uden square. The references are given there. You could also use a row column design if you wanted to. And then one modification of interest is the modified augmented designs. You see at the bottom, these actually use systematic placement of controls, which it has some desirable features. There was a type 2 modification was particularly for the case where you have long rectangular plots, like as you see in the picture below there. Those are some barley test plots, and the barley breeding program here is using these MAD type 2 designs in the preliminary stages of their breeding program. Other possibilities would include an augmented split block. Say, for example, you wanted to test not only new entries, but also look at adaptation to different, say, different stresses. You wanted to have a well-watered and a drought-stressed treatment. You could combine those in factorial combinations of treatments could be analyzed with the augmented split block. If you had a large number of checks you wanted to include in the experiment, you could use an augmented lattice square or an alpha-alpha lattice, and references are provided there. Interesting paper was published recently on augmented p-rep designs, and because the feature of this is that you would actually replicate some but not all of your new entries, and then you might do this across multiple sites. So say at one site you might replicate the first 10 entries, and then at another site the next 10 entries, and so on. So by the time you collect the information from all sites, everything would have been replicated at least that second time. Yeah, so then because you have the replication of the entries, it's not necessary to include all of the controls that we typically include in augmented designs. There's also information published on how to combine information across sites. As you can see, the Federer, Reynolds, and Crosa reference there. And then additionally, some of you may be interested in combining trend analysis with augmented designs, and I would then refer you to a couple of articles that are in the supplemental list of references, a book that came out in 2003 that has a couple articles by Federer that show how to combine both the trend analysis and the augmented designs. If you're actually going to go and use augmented designs across locations, you have the option also to use lattice designs, in which case you could consider your sites to be complete replications and then have one rep of a lattice design within each location. The advantage of this is that then you're using information from all of your plots to adjust means for field effects. So I don't know this with certainty, but it seems likely that you could have greater precision to detect differences among your entries in that situation. However, there are other situations where you might prefer to go ahead and use augmented designs across locations. One desirable feature is that you have very flexible arrangement of new entries in your field plans. I read one paper where for participatory plant breeding, for example, where you could actually have growers recommending varieties, different augmented varieties at different sites. You could also then obtain an estimate of experimental error from each location. So you could use this to assess your site quality, to do analysis of G by E interactions, and then at the end of the day you have more flexibility in deciding how you want to do your cross-site analyses, which sites you want to combine together. I searched around for software available for analyzing augmented designs. The AgriBase has a nice feature for looking at the MAD type 2 designs, and then that's what the barley program here is using. There were some software is available from the Indian Agricultural Research Institute. They also had published some SAS macros. CIMMYT had a SAS macro available online. I couldn't get it to work. Some of the SAS syntax was outdated, but again, that would be, if you were going to develop your own macro, that would be a starting point. So as I said, I have provided a full list of references in the supplement. These are the two references that I used most extensively for this presentation. And I'd also like to acknowledge then contributions, the financial support from USDA CS3s. We had a special grant for Meadowfoam research at the time of this experiment was conducted. The OMG Meadowfoam Oilseed Growers Cooperative. We also get funding through the Paul C. Berger Professorship Endowment. I'd like to thank the Crop and Soil Science Department here and Meadowfoam staff that help with our research. Okay, I'd be happy to take some questions.
Thank you very much, Jenny. And again, I very much appreciate you being able to soldier on. I apologize for loading the wrong presentation.
It probably went a little faster than it would have if I had it, the updated presentation, but it's no problem.
Well, again, my apologies.
All right.
So we have about 15 to 20 minutes to answer your questions today. And for those of you who missed the beginning of the presentation, you can use the question box on your screen to type in questions and hit return. If the question box is closed, you can click the small plus sign next to the word question to open it up. We'll be reading the questions out loud and we'll answer as many as we have time for. And as Jenny mentioned, and as well as was mentioned during the webinar, the presentation, dataset, SAS program, as well as the full list of references and resources that Jenny mentioned towards the end will all be available online at eextension.org. And at this point in time, the resources, except for the webinar recording, should all be there. So please feel free to make use of those resources. We're making them publicly available so that they are there for anyone to use, and we hope that you'll find them useful. So the first question, Jenny, is one that you and I have talked about a little bit, and I'll just touch on briefly, is whether there's an R package available for augmented design. And
okay.
I could let you go first. You're
yeah, I'm not aware of that, but you've looked into that more than I have, so why don't you go ahead and answer that question.
Yes, I was going to say, to my knowledge, there is not an R package available for augmented design. One of our future objectives is to develop an R script based on Jenny's presentation today, so that we will make that publicly available to people. As well, at Plant Breeding and Genomics, we have a lot of interest in R, so we would like to share whatever resources are available. And we've got a few more questions here. One question, Jenny, and I'm sure you'll have to qualify this, is what's the minimum required number of checks?
Yeah, that really depends on what crop you're working with, what traits you're working with, how heritable they are. You know, the rule of thumb is that you need to have 10 degrees of freedom for error. So you have to balance your number of blocks and number of checks to you know, get that value of 10. But that's just a minimum value, and that, for example, in corn, I know from having been worked a lot as a corn breeder, you need a certain plot size, minimum plot size, and you also need a certain number of reps to get be able to pick up significant differences among families, say half sib families or full sib families, for yield. So I wouldn't, I think even if you had quite a lot of checks, you would potentially not be able to pick up differences for yield in corn with a single rep. So in that case, you know, there's no way to really account for the fact that you don't have multiple observations to estimate your means for the families. So I guess so ballpark would be 10, but that, you know, in some cases that won't be sufficient, and in other cases where you have a highly heritable trait, you know, you almost wouldn't even need to have 10 degrees of freedom.
Great. Thank you, Jenny. And we've had a couple more requests for the link to the presentation, so I've typed that into the chat box.
Okay.
And there's one comment here suggesting that genetic reps in large families may help make up, I believe, make up for some checks, I believe.
Yeah.
Yeah.
Yeah. I think perhaps they're thinking about the case where you'd be looking at taking data on individual plants, and that would be then constituting your family. For Meadowfoam, we're looking at a plot mean basis. So or else I'm just not quite understanding the comment. Oh. Yeah.
Sorry. Okay. So the actual genetic replication in large families. Genetic replicates substitute for technical replicates in detecting your trait differences and increasing your heritability.
Okay.
That's the suggestion.
All right, I'll have to think about that.
Yeah.
Think about that. Again, that may be referring to a case where you're taking measurements on individual plants within each family.
Sure. Yeah, my apologies. I got us on a little bit of a digression there. I apologize. We had another nice comment from someone saying that they know of a package in R called DIGGR for designing P-rep trials.
Well, that would be of interest. That's sort of it's still an augmented design, but basically without the checks, because you're just using some of the replicates. I mean, some of the entries as repeating some of the entries, replicating those so that they act as, they give you the estimate of standard error that you need. I haven't worked with those, but they looked very interesting when I looked at that paper.
So thank you very much for that comment. And another question is, are you aware of other researchers at OSU using augmented experimental design in their breeding work?
At OSU, well, the barley program is the one that I know about. I know, for example, when I was working in Africa, they were using augmented designs in cassava, and that was, in the particular case, they had, there was a cassava mosaic virus epidemic in East Africa, and they needed to move some resistant varieties from West Africa over to East Africa, but the varieties had very different quality and growth properties, the new varieties. And in East Africa, the farming systems were quite different, so they used augmented designs to evaluate potential new introductions in that area. That's one case I know where augmented designs were used very effectively because they weren't limited in seed. It's one of the reasons that we use augmented designs, but they were wanting to test as many different farming systems and environments as they could. So that was one very nice application of augmented designs. I don't know of any other breeders here who are using augmented designs, but there may be some.
Great, thank you, Jenny. And we've got some more technical questions here for you that you can do your best with. A nice question here, actually. If we are testing a large number of entries at several locations, do we need the same checks across all locations, or can we do some common checks and some checks for specific locations?
I think you could do it. I think you would have options. You're going to get an independent estimate of error within the location, and so that it would kind of make sense to do that. In fact, if you wanted to use additional checks within each location that maybe had specific adaptation to that location, you could use that to get a better adjustment of your block effects there within the environment. But you might have some broadly adapted varieties that you would use across all of your locations, and that would be then a nice way to tie together the information from the different sites. So that would be seems to me to be a very reasonable approach.
Mm-hmm. Great. And then a question here about your breeding program.
Mm-hmm.
What acreage is required for your Meadowfoam research?
We're a very small scale program because the current production of Meadowfoam in Oregon is only about 5,000 acres. So this is a crop that's been used because of its potential, and the real constraint for us is the markets, developing the markets for the crop. As I said, it's currently used in the cosmetics, and the use of Meadowfoam in cosmetic products is gradually increasing. But presently, some of the other industrial applications are not, in practice. So limited acreage. So we have a very small scale project. So I'm usually only, maybe 3 acres or something per year, plus all of my isolated seed increases and so on.
Great. And we've got a nice comment here from the wheat breeding group at the University of Kentucky, and they say that they have been using an augmented design to test yield in early generations when they don't have large quantities of seed.
Right.
And they, yeah.
Mm-hmm. Yeah, I had in my in the most current version, I had wanted to make that comparison, particularly for, as I said, like in corn, I would be reluctant. I would rather have, say, 200 families with 2 reps per site than 400 families with single replicate, just because I know that I wouldn't have very much chance of picking up detectable differences among my families with just a single rep. But in a crop like either a clonally propagated crop or one, an inbreeding, self-pollinating crop where you're using some sort of pedigree selection system, when you put your initial material out in the field that's just the first go at it. So, for example, in Oregon here, we have a lot of difficulty with stripe rust in barley. So in their early generations, main objective may be simply just to get rid of stripe rust susceptible lines. So, but then they know they're going to advance that material another generation and can do more in-depth screening in subsequent years. So that's really an ideal situation where you'd want to, be able to, in order to be able to test as many genotypes as possible, you might want to use a single rep in the first year of evaluation. So it depends on the crop and also on the heritability of the traits of interest.
Sure. And you got a couple nice thank yous from both grad students in the Moose Lab at Illinois,
okay, well,
and
you're welcome.
as well from the wheat breeding group in Kentucky.
Okay.
And we have another question here asking about outliers.
Okay.
And wondering if they should be, or does it make sense to remove outliers based on the residuals of unreplicated entries across multiple locations?
It doesn't. I don't know how you would do that, because you really only have the residuals estimated for, if you're doing an ANOVA analysis at least, you only have the residuals estimated for the check entries. The new entries don't have residuals. They're all 0. So I guess you'd have to have some other means other than a typical residual plot to figure out what really, was just an improbable observation. Yeah, I really don't know what else to say about that, except, if you have something that's completely out of the ballpark, then you may just have to throw it out. But I'm not quite sure what criteria you'd use to decide that.
Mm-hmm. Great. Well, we have a little bit more time for questions if anyone has things that are still pressing. And I see here, I will actually share the links again. Let me try this again.
It may be a good idea also to check and see which version of the presentation was posted.
Yes, and I did check. After we had the mix-up, anyone who is still on, I did update the presentation.
Okay.
online.
So if they printed it out before the presentation, they probably had the older version?
Yes, they would
Okay.
want to go back.
Mm-hmm.
And we have one more question here. I don't know if you want to comment specifically in wheat and the number of checks that you may be looking at. You know, we've talked some about how it depends on the trait and the heritability of a trait.
It also would depend on the block size that you want to use too. Different crops, you know, and also if you have some sense of the environments that you're working on, the field heterogeneity that you have to account for. You know, once you've been working in an area, you kind of get a sense of, well, you know, if I go above, say, 20 entries in this particular crop, this particular site, I'm likely to have too large a block size to get good comparisons within blocks. So it would also depend on, you know, how big your blocks are and how you need to represent, have checks representing that area.
Okay, another thank you here to you, and also a question about using augmented designs for QTL or association analysis. Are you aware of anything in that area?
Well, in the barley cap program, some of the data that we received from the Oregon State breeding program was based on augmented designs. So, and then the objective of the Hordium Toolbox, the database that was developed through that project, was to do association analysis, look for marker trait association. So I guess that would be one example. I don't know specifically of other examples, but that would be one case.
Sure, okay. And you have a thanks from a former OSU barley grad as well,
Okay.
who was able to join us today.
Mm-hmm.
So, okay, here's another possible suggestion when we're looking at number of checks that we may want to use.
Mm-hmm.
That there's a suggestion that this person has read that they thought you should have at least the square root of the number of new entries.
Yeah, I've seen that too. Yeah, I've seen that. I don't, you know, I think in the information from the Indian Agricultural Research Center, I gave reference for their software and so on. That's they do have capability in their little package to help you estimate that using that criterion.
Great. And coming back to the question regarding QTL and association analysis, we have a comment here that Fusarium head blight was scored using an augmented design, an association, or QTL analysis.
Right. Mm-hmm.
And another nice comment here that augmented designs help us to increase our genotypic replication, though at the expense of our line replication.
Mm-hmm. So thinking of perhaps like an F2 family to represent have numbers of individuals from that F2 family rather than the individual lines coming from the population.
And another question, could an augmented design be used for selecting lines from wild accessions with small seed amounts compared with checks?
Yeah, I think that's one possibility. In fact, again, with the materials online from the Indian Research Center, I forget the specific name, but they also mentioned that as being a primary use where you're getting in new accessions from, say, gene bank or something like that, and you don't have much available. So that would be a very appropriate use of augmented designs.
And one comment, or one question that relates back to the design in our field space, the question is, across locations, field size restrictions may apply. How would you take that into consider while you're designing your plots?
So you're saying maybe there at one particular site you have smaller area available than at other sites. Well, I think there wouldn't be. Yeah, I think I'm just trying to think off the top of my head here. Yeah, I suppose if you're going to combine information across sites, it would be desirable to have the same plot size, to have common variance. But I'm not really entirely sure about that.
Sure, and I would think off the top of my head as well that you would want to maintain, say, the same plant spacing across locations as well, I would imagine.
I do remember from one of Federer's papers that the common variance was not essential, but that's all that I could say.
Sure.
So that there's one reference there, that 2001 paper, I think it is, where they combine information across sites, and that was a comment he had that would not be essential, but I guess I don't quite understand why that is.
Okay, and we have one more question here regarding the square root guide that we mentioned briefly. So if you use the square root guide, is that the number of reps of a check variety or the number of different genotypes?
Yeah, that's a good question. I don't actually know which one that refers to for that particular rule of thumb. I prefer to use the minimum number of degrees of freedom for your ANOVA criterion, in which case you can adjust your numbers of checks and reps, to obtain that minimum number. So I'm not sure for the other criterion which one that refers to.
Sure. And it looks like we are just about out of time for questions today. And please join me again in thanking Jenny for a great presentation. And as well, I invite you all to join us for future webinars. And we are planning to provide a second or part 2 of the augmented design in future, hopefully in the next several months. And if you'd like to stay up to date with webinars put on by the Plant Breeding and Genomics Community of Practice, I would encourage you to sign up for PBG News, and that's our newsletter, and you can sign up at pbgworks.org. And if you still have any questions that are particularly burning, you may email them to me at merk.9@osu.edu. Thank you so much for joining us today, and please don't forget to fill out the survey evaluation.